All right, guys, we're moving on to our next chapter, which is on the structure of molecules. And specifically, what you're going to learn in this course is something called Lewis structures. Okay, these were first introduced by somebody named G.N. Lewis in the early 1900s, and they connect some of the properties of quantum mechanics and electron configuration and try to basically embody bonding, okay, chemical bonding in a very simple way, represent chemical bonding in a very simple way. And so kind of just very broadly speaking, there's a lot of different information that you can get from these Lewis structures. One is just very simply thinking about like number of bonds in the molecule. And compounds and molecules can range from something very simple like diatomic hydrogen, where there's one bond, to something like DNA that has, thousands of bonds, right? Or a polymer or a protein, okay? Within that bond, you can think about bond order. And so you'll see this when we draw these Lewis structures, but it's reflective of how many electrons are being shared. So in a so-called single bond, 2 electrons are being shared in that bond. And that will have a certain strength. A double bond will be stronger, and 4 electrons will be shared, and a triple bond will be even stronger than a double bond, and 6 electrons will be shared. So you can get that information from these structures. You can also get something called resonance out, which tells you how the electrons maybe are delocalized across the whole structure. Those electrons in a bond could be shared across multiple atoms, as we'll see. And that ties into electron distribution. Where the electrons are they on certain atoms? Are they being shared across a molecule? Are they being shared across a different bond? And all of these things together give you a lot of information about chemical reactivity, which ultimately is what chemists are interested in one way or another. It all comes back to chemical reactivity. And so within that, we'll be able to use these structures to predict the geometry of the molecules. That will be done in the next chapter. And that gives us information about the shape of the molecules, something called polarity, which is how a charge is distributed, pluses and minus charges are distributed. And that gives rise to physical properties, which we'll talk about at the very last chapter of the course. Things like how soluble compounds are, the vapor pressure, right? How fast they can evaporate, basically, or the pressure of evaporation, and their boiling and melting points. So it's pretty crazy. And this is, the beautiful thing about chemistry is that in this course, you're taking one course, very introductory course, and yet you're going to be able to go from quantum mechanics, the fundamental properties of the universe, fundamental equations of the universe, and then be able to use that all the way to explain natural phenomenon of you're gonna be able to say, why does water boil at 100 degrees C, or at least roughly. And so to me, that's just fascinating and extremely powerful thing about chemistry, is that with very basic principles, you can really make a lot of powerful predictions about the natural world. Okay. And so this is why we're studying this Lewis structure topic and why it's so important. So central to all this Lewis structure business is valence electrons. We're talking about bonding here. And so you're really going to have to hone in your understanding of valence electrons, right? And that depends upon its electron configuration, which on the periodic table, since the periodic table is shaped in a way that is based upon the electron configuration of the elements, that you can use this, basically look at the columns, right? The alkali metals are going to have 1 valence electrons. They like to form, remember, +1 charges to be like the noble gases over here. The alkaline earths, group 2, column 2, are going to form +2 charges. They have 2 valence electrons. And then 3, 4, 5, 6, 7, till you get to the halogens. At 7, they want to gain 1 electron, right? Octet rule. Or they could lose 7 electrons. That's very unfavorable and become like the previous noble gas. But instead, they're going to become anions, right, and form 1. but they have 7 valence electrons because of that. They're much closer to this side than they are to the previous noble gas. And the noble gases has 8. An exception is helium, right? Because there's no 2p orbital. Quantum mechanics tells us there's no 2p orbital. And so helium is a noble gas with a filled 1s2, and it only has 2 valence electrons. So carbon, if you look at your periodic table, that's right here. So it has 4 valence electrons. Fluorine is the first halogen, so it has 7 valence electrons. Okay. So valence electrons are in the outermost energy levels, the outermost principal quantum numbers, and those are the ones involved in bonding. Notice that I didn't tell you anything about the valence electrons for the D block or in the F block. The lanthanides and actinides aren't even on this periodic table. You'll have to take more advanced chemistry courses to learn about the structure and bonding of those compounds. It's a little more complicated, but the basic principles are still true. Okay. So we're not even going to worry about number of valence electrons for transition metals, for example. So remember Dalton's atomic theory. We went over this in chapter 1. Each element is made up of tiny particles called atoms. We know that the atoms of a given element are identical. It's roughly true. Of course, there's isotopes. And then the third part of this was that atoms combine in simple whole number ratios to form compounds. Okay. So you can't have a fraction of an atom. That's what this is saying. And we're going to form compounds like carbon dioxide, where we have 1 carbon atom and 2 oxygen atoms, and water, where we have 1 oxygen and 2 hydrogens. Okay, but how do we get there? How did you take hydrogen and oxygen and then make a water molecule? How does that happen? And in order to figure that out, you're asking about bonding when you ask that question. You're going to need to know the electron configurations of the individual elements and the number of valence electrons. That's kind of follows from the electron configuration, right? And so we're talking about bonding theory here. And this predicts how atoms are bonded together. And we're also going to be using something called Lewis dot structures. This is basically just a nomenclature, a pictorial representation. There's many different ways to represent bonds, but how we can represent bonds using pen and paper, okay? Obviously, you can't see bonds with your eyes, okay? There are ways to look at bonding motifs using various experimental techniques like microscopes, not a light microscope, but other advanced microscopies, okay? But this is just a way for us to visualize it or conceptualize it. It's not visualizing it, okay? It's conceptualizing it. All right, so let's look at oxygen, for example. We're going to talk about these Lewis dot structures as just a beginning to get us set up for bonding. So oxygen has that 1s2, 2s2, 2p4. It has 8 electrons, and that's the electron configuration. The ones in the valence are the 2s and the 2p's. They have an n equals 2 energy level. And so they have 6 valence, oxygen atoms have 6 valence electrons. And so how are you going to draw the dot structure? You just draw the atomic symbol, oxygen, right? Write that down. And then you're going to add the 6 electrons. And notice how I did that? I singled them up first and then pair them, okay? And this is trying to get at the fact of Hund's rule, right? The fact that, electrons don't want to be paired unless you have to pair them. So when we draw the electrons as dots, we put 2 electrons per side, but we write them singly first, and then we double them up. And so we can practice this writing Lewis dot structures for different elements: argon, silicon, nitrogen, and chlorine. You're going to want to look at a periodic table for all of this, right? And recall that if I bring in a periodic table here, let me make this smaller. Right, so argon is a noble gas, okay? So that's going to have 8 valence electrons. And so we would just write 8 electrons on 4 dots. The argon's happy like that. It's stable. It's following the octet rule. It's a noble gas. It's not going to form a compound. Silicon is right here. It's in group 4, the 4th group, right? It has 1, 2, 3, 4 valence electrons. So how would we write that? Just like that, okay? 4 separate electrons. We didn't pair them up. Nitrogen. Nitrogen has 5, right? 1, 2, 3, 4, 5. So again, don't pair them up unless you have to. Once you get to the 5th electron, you're going to have to pair it up. It's going to look like that. And chlorine's a halogen. It's 1 electron away from argon, right? It's going to have 7 valence electrons, and so they're all paired except the last one. All right, so that's it for this video, guys.